Martínez Díaz, an engineering student at Pontificia Universidad Javeriana. Today I'm trying to share our final project, a low-cost three-dimensional scanner design for students. Our goal was to make three-dimensional scanning technology accessible using affordable components, costing less than $100. In this video, I want to track the hardware, how it works, define the state machine that controls it, and the lesson we learn. Let's do it. Our scanner is built with a few key components. At its core is the ESP32, the microcontroller, the brain of the system, controlling motors, reading sensor data, and communicating with a computer. We program it in C using the Arduino framework. For precise movement, we use two stepper motors, each driven by a driver with 1/16 microstepping for smooth motion. One motor rotates the platform 360 degrees, called theta movement, while the other moves the sensor vertically, known as Z-axis movement. To measure distance, we choose the infrared sensor, which detects objects from 10 to 18 centimeters with 1 centimeter accuracy. It's affordable and fits for educational goals. We also include limit switches to keep the Z-axis within safe limits, preventing collisions. The mechanical structure, including the rotary platform and the Z-axis, is 3D printed, keeping costs low and allowing easy customization. The scanner operates by rotating an object on the platform while moving the sensor up and down in 20 steps. At each position, the sensor measures the distance to the object, and the ESP32 calculates 3D coordinates using these equations. Here, theta is the angle in radians, current J is the current high level, and the total vertical distance is 10 millimeters. These coordinates are sent to the computer via serial communication at 1,200 baud, or custom visualization software, built in C with the Raylib library in code blocks, renders and 3D point cloud in real time. Users can rotate the model, switch view on models, and see points colored by high. Red for low points and blue for the highest one. The entire scan takes about 20 minutes, reproduces around 6,400 points, perfect for the occasional use. To keep the scanning process organized, we implement a finite state machine, FSM, on the ESP32. The finite state machine has 5 states, each handling a specific part for the process. The first one is the state setup. This state initializes the system, ensuring the Z-axis is at its lowest position, using a limit switch. The limit switch that we talk about later. If it's not there, the Z-axis moves down until it's already. Then transitions to the next state, that is a state moving theta. The platform rotates 360 degrees, with the motor taking 3,200 microsteps for precision. Every 10 steps, the sensor measures the distance, and the ESP32 calculates X, Y, and Z coordinates, sending them to the computer. After a full rotation, it moves to the next state, that is a state moving Z. This state moves the sensor up to the next high level, taking 20 microsteps per level, about 0.526 millimeters. After reaching the new height, it returns to a state moving theta to scan that level. The cycle repeats for 20 high levels. And this state go to the state return home. Once all levels are scanned, this state loads to the Z-axis back to its starting position using the limit switch, preparing for the next scan or shutdown. State finish is the last state. This state signals that the scan is complete, the motor stops, and the system waits for a reset or further instructions. The finite state material ensures a logical flow, preventing errors like a misaligned movement or incomplete scans. Each state has its own function in the code, like handle setup or handle moving theta, making the process robust and repeatable. Our scanner successfully captured points clouds with about 6,400 points, with the accuracy, of course, but with testing on an object like a small sphere, achieving the same results, though with some noise due to the sensor limitation. And of course, we face some few challenges, like the motor wear, the rotation motor wore out over time, causing vibration and reducing accuracy. This talk has the importance of the durable components and investigate the importance of the investigation of that components. Sensor limitation, the infrared sensor stopped with a reflective or transparent surface like glass, leading to errors up of some millimeters. Software performance, our visualization software slowed down with large data sets and lacked advanced features like mesh generation. These challenges were great learning opportunities, helping us understand mechanical design and sensor technology better. Of course, help us understanding how is the life of the engineer to live with that, and maybe to take the scanner to the next level. We plan to replace the infrared sensor with a local lidar for provide accuracy, structure the mechanical structure to minimize vibration. Because the software, we can do it better with features like mesh generation and texture capture. Develop a user-friendly graphical interface to make the scanner more accessible. Of course, this is a good project that you can do it in your home, and for prove your abilities in programmation and learn to use Arduino in other ways.